Hey everyone. So I'm Michael. I'm co-founder and CEO of Fabric Cryptography. And today we're going to be talking about how an architecture that we designed for zero-knowledge proofs can actually be used for fully homomorphic encryption as well. So just a few words on our company. We have over 60 people. We're a very recent startup. We're executing one of the fastest tapeouts ever. And we started January last year. Already we have about $40 million in equity funding, a couple more actually coming in. And we have quite a bit of customer orders. And we're actually coming to market very soon. So hardware is coming way sooner than a lot of people realize. Our team actually is an AI hardware team that comes from all sorts of backgrounds. The Google TPU team, we have team members from NVIDIA, we have team members from Galois. So really at the intersection of hardware, software, and cryptography is where we are.
And also the chip takeouts and patents help, that's from like people's backgrounds and obviously not from the company.
Yes. So really what we're going to talk about today is what if the secret to speeding up zero-knowledge proofs and fully homomorphic encryption was really the same thing? What if we could create a general-purpose architecture for all of cryptography? And so our first processor for zero-knowledge proofs, we had 4 main goals. The first goal was achieve really high performance. The second goal was general purpose. We wanted to cover a whole range of cryptographic primitives, and ideally we would cover TFHE as well. We wanted to be easily programmable. We wanted it to actually be even easier to program than, let's say, a GPU or FPGA. And we wanted this to be entirely scalable, right? So this should be a mass-producible piece of hardware that is deployed in dozens of data centers worldwide in its first year of existence. So this is really where we wanted to head with this. As a feature of kind of where the blockchain market is today, zero-knowledge proofs were kind of the first target. So our first goal was real-time ZK proving with end-to-end acceleration on chip. And so we put the primary focus there because of the market, but thanks to this market bootstrapping our company, now we're in a very good position to be able to provide these accelerators to FHE-focused companies as well. So we have a full graph compiler, we have a full LLVM compiler, we have a whole library of kernels like NTT, and we're going to be using the graph compiler to basically compile these kernels and compose them into entire end-to-end workloads. And so following a model very similar to the AI hardware companies that you guys might be familiar with. And our intent is to ship thousands of ZX100s, which are the the server machine next year, and make VPUs available on the cloud as well. So for blockchain applications, this could be a cloud validator that you can basically start a node over the cloud without any effort setting up hardware of your own. Now, there are many chips that accelerate cryptography. We have GPUs, we have FPGAs. We have a lot of ASICs also coming. I know that FHE has quite a few chips coming out, especially from companies in the US, but also from a couple companies in Europe. So that's all very exciting. The VPU is the only chip that really is programmable, right? So from day one, what we really wanted to create was essentially a GPU for cryptography, right? So if you look inside the computer architecture, a GPU is based on programmable vector instructions, right, in a SIMT architecture. We wanted to target something much more like that and much less like the FPGA. So the FPGA, you have to place and route things. You have to figure out, essentially, in the newer FPGAs, you have DSPs, integer blocks that you can route together. And in kind of older FPGA generations, you have just lookup tables. What we wanted to do was have a normal style of programming that end users can easily access and play around with performance models. And then the last thing is, there are a lot of ASICs coming out. I think a lot of these are actually funded by DARPA. You know, one distinguishing feature of the VPU is, you know, we're not just targeting a limited range of radix sizes or a limited range of workloads. We actually want to support basically anything that you want to do because we basically have an architecture very similar to the GPU. And so Gen 1 of the VPU, we have dozens of supported primitives. You know, we have modular field arithmetic of all sizes. We have NTTs. We have, you know, LDEs for ZK. You know, we've done all sorts of things basically in the VPU to support all sorts of different primitives. Really what we did was we broke these primitives down, and what you really see is that basically all of them break down to big integer operations, right? So we have 10x the big int ops as the GPU. And we also have a terabit per second CPU to VPU interconnect. And so if you look at our die photo right here, we actually, this is the right side of the die. We have a giant RISC-V complex. And then the RISC-V complex basically has an on-chip interconnect, and it can boot Linux. So basically, the end-to-end code, including the host, can all run on the same chip. This is another point kind of from the easy-to-program aspect. And then if you look inside the VPU tile, right, this is the constituent core of the VPU. We have a bunch of these. You really see a very typical vector processor, except with custom instructions and a register file tailored to cryptography, right? So you have scratchpad memory. This is all software managed. You have separate banking for every 64-bit lane. And so every lane can basically access its own scratchpad memory, its own addressing. So every lane can access a different address, even if it's the same instruction. We have a register file that natively has kind of equal read ports to write ports. So this supports really, really efficient butterfly operations and things like that. And then we have basically a bunch of ALUs. These are cryptographic ALUs. They're, you know, modular field arithmetic built in. You know, we actually have a single cycle Goldilocks operation, and we also have a 3-cycle Barrett operation for just arbitrary prime fields. And then basically these SRAMs can be linked together. And so every VPU tile is architected to perform essentially very, very high-speed number theory, right? So this is basically the chip on the right-hand side. It's a flexible 2D network on chip that uses a graph compiler to lay out these parallel workloads. So as an example, if you have, let's say, one NTT kernel, then to alleviate your memory bandwidth, you can break down your high radix NTT into a bunch of small radix NTTs, and you can actually tile them across the chip and ensure that you stay entirely local to the chip during the entire end-to-end NTT. And you know, what we found was that even though we didn't really target FHE that hard in terms of our product requirements, the primitives that we already supported for our ZKPs translated pretty well to FHE. So this was a really cool result, one that we suspected would maybe happen, but we were really thankful and happy to see that it turned out that way. So on the left, you see some of the primitives that, you know, ZKPs have. ZKPs also deal with a bunch of polynomials. ZKPs also deal with a bunch of number theories. ZKPs also deal with a bunch of NTT. And you take some of these operations and you look at FHE, you basically have actually a pretty good subset of these operations. So, you know, linear algebra is used, for example, in the Poseidon 2 hash function, where the MDS matrix is multiplied by, you know, a vector. You have this kind of stuff in FHE. You have dot products, you have point multiplication, and then you have NTT, which, you know, is 80% of the workload. And it's also a pretty substantial portion of most ZK algorithms as well. So, you know, it lined up pretty well.
Where did you use point multiplication in FHE?
Sorry?
Where did you use point multiplication in FHE?
Oh, sorry. This is not elliptic curve point mult. So, so actually, I think this slide might have been created in a hurry, and we might. Yeah, no. There's no intention there. Any other questions? Cool. And so one of the things that happens in chip architecture is you're really looking at how many of the transistors you're using, or what fraction of the transistors you're using from the beginning of the workload to the end, right? And so the trade-off on general processors is that you have AI, you have crypto functions, right? Let's say it's GPUs, or let's say whatever it is. You know, you're using some of those functions some of the time, right? So you have an IPC probably of sub 1, and you have certain functionality, certain instructions, certain die area that you're not even using, and so most of your die is just wasted, right? And so this is the trade-off of general purpose, is if you can't get enough circuit reuse, and you can't get enough throughput efficiency in IPC, or if you run into some sort of memory or I/O bottleneck, you have a problem. And so one thing that we really focused on with the VPU is how do we make this general purpose enough to be able to target lots of workloads? And so we actually share the multipliers between the 64-bit and the 256-bit, 384-bit stuff used for elliptic curve point add and things like that. So basically, a lot of the circuitry, although it supports different instructions, is actually shared between the different instructions. And so what that ensures is that, you know, not 100%, but, you know, a quite high proportion of the area is used, and it's used 100% of the time, right? So that's kind of how you can think of it as the overhead versus a fixed function ASIC. And that overhead is something that you pay in order to get algorithmic improvements well into the future. It's an overhead you pay for the blank canvas that it gives you, the ability to try out basically new ideas. And so this is the FC1000 chip. You know, it has 40 tiles. It has 5 channels of really high bandwidth GDDR. It has an 8-core RISC-V complex and a PCIe 4.0x16. And so tons of bandwidth, both internally and externally. And the bandwidth is very well matched to the die area. So actually about half of the die area is made up of PHYs alone, so made up of transceivers sending and receiving data alone. And so basically one thing that we looked at was how big of an architectural lift you actually get from doing much more compressed instructions from, you know, normal instructions. And so usually in modular arithmetic, you'll have to do, you know, a set of 3 kind of Barrett things, or maybe a set of Montgomery things, right? And so when you do those methods of reduction, you have to do many, many multiplies, and these multiplies are not very well pipelined on the CPU. You can't do an add at the same time as a multiply, you know, so there are a lot of unique features of our microarchitecture dedicated to specifically the art of doing modular arithmetic. So, you know, fewer instructions equals faster computation, and that's basically how we designed the VPU instruction set. So here are some specifics, right? This is with our current cycle-accurate model of our kernel. So on the right-hand side, we're benchmarking TFHE, and we achieve right around a 63 millisecond execution time at a cost per hour far south of an FPGA, right? So I think right now we're sitting at about 20x, and this is rather unoptimized. So, you know, we're being the most intellectually honest we could possibly be. We're using a cycle-accurate model, and there are a lot of optimizations that we have yet to really apply. And really, our flexibility in this architecture helps, you know, everyone change algorithms pretty quickly. So in ZK, the way this shows up is you have a lot of different proof systems, and you have a lot of different primitives that go into those proof systems. And in FHE, you know, swapping out the parameter sets easily is something that you want to do ideally per circuit, right? So for different FHE circuits, you have different levels of noise accumulation and things like that. You know, you might want to do different things. And so what we're able to do is, you know, with this programmable chip, instead of being like, okay, we target only this set of radix sizes or only this set of precisions, you know, we're as general purpose as we can be. And so, you know, the VPU is basically designed to be much, much better as a baseline. You know, if we translate kind of the current implementations in the literature over to the VPU. And then, you know, what's achievable is even beyond that, you know. So for example, like the current Zama library is written for FFT, and so uses a lot of floating point, and as a result, noise accumulation happens relatively quickly. The VPU has NTT, and it has high precision NTT, and it has this hardened. And so basically, this means that we can do so much NTT that, hey, like maybe we can use the fact that noise accumulation happens much more losslessly in order to change some of the parameters on here. So that's kind of one high-level optimization that we have yet to factor in, just how often the bootstrapping has to occur. And you know, one thing that people always ask me is, when is this coming? And we're really proud to say that this is coming in 6 to 12 months. So, you know, we just announced on stage the other day at the Polygon event, judging by this audience, probably a small intersection. But at that event, we announced that real-time ZK proving was being brought to the Polygon ag layer by the VPU. We hope that we can do a similar leap in the FHE space, but maybe not real-time yet. And so this is actually shipping at scale early next year. So this is the final card. You know, we have 3 chips on there. This is fully routed, and it's ready to be handed off to a contract manufacturer. The chip is in the final stages of backend. And so we hope that with Fabric hardware and your research, we can make some new leaps in FHE. Our colleague Thomas used to be at Zama and KU Leuven. He's also in the audience right now, so feel free to reach out to him if you have questions about specifics or if you're curious about opportunities to collaborate.
Any questions?
Yep, go ahead. Never mind.
So, yeah, I went first. So you gave some numbers and you said they were TFHE, but you were talking about NTTs. So you're using an NTT version of TFHE or an FFT version? Because you didn't seem to mention FFTs in your talk at all.
Yes.
They're similar, but they're not.
Yes, of course.
They're slightly different, yeah?
Yes, so this is an NTT-based version of FHE, but running the same set of parameters as the FFT version. Is that right, Thomas?
Yeah, that's correct.
Yep.
So basically you use the NTT, you kind of use a big prime to take the NTT to make the FFT. What's that, sorry?
The Goldilocks prime. So the micro switch, like for the FFT, you go to the...
Oh, I see. Okay, yeah.
For everyone in the audience, Thomas just clarified that it's the Goldilocks prime that we used.
Yeah, I had a similar question. I think it was slide 13.
13, yes.
What exactly are you comparing here? What's the application running?
This is programmable bootstrapping.
Oh,
So,
programmable
you know,
bootstrap.
yeah.
The FHE unsigned integer 64-bit.
Yeah, FHE uint64 multiplications. Yeah.
How did you calculate the cost per hour? Because the other ones are including Amazon, like the cost of renting the server and this kind of things. So how did you calculate the cost here?
The cost in our case includes the cost of amortizing a really, really expensive hardware development cycle. So I think there are some features of the cost that are kind of similar in that the marginal cost is not the same as the actual cost to the company. But we anticipate as time goes on, the same piece of hardware is going to come down very substantially in cost.
But there's also, of course, like energy costs and this kind of things that you...
Energy cost is actually pretty marginal when compared to the CapEx. So we anticipate that energy cost should be around 5 to 10% of the entire thing.
Hey, how's it going?
Hey, good.
How fast do you think you'll be able to get those numbers? Like, what's the theoretical limit in terms of latency? Hey, Thomas.
The theoretical limit in terms of uint64 latency on the VPU, is that what you're saying?
Yeah.
I would say that it's hard to tell because I know Zama has like an internal tool that does a lot of this like parameter swapping and things like that. And what we've been told is it's highly unpredictable in that you know, if we put noise accumulation and then we put like a specific circuit, then we could actually get like a theoretical estimate of how far it can go with like some parameter optimizations. But we haven't tried that tool out yet or anything, so I think that would be a more involved exercise that we're really excited to dig into.
And in terms of hardware, so not changing any of the parameters, just making the hardware faster potentially over time, how far can you go?
So our next gen hardware, we hope will be on a very low node. So we're talking about something like 7 nanometer, 5 nanometer, 4 nanometer, something like that. So we already are working with the fab to get basically plans set up for that. And that's going to begin the architectural design in a couple months. So yes. Sorry?
Thanks.
This is 12 nanometer. So the next gen should be several, you know, at least one, probably several orders of magnitude beyond this. Any other questions? All right, wonderful.
Yeah, thank you, Michael.